Am I audible?
Yes, ma'am, audible.
SCMS procedures.
सर मैंने पिछली बार क्लेम लिया था
Good afternoon, all. We are back yet again with another interesting session on the day 2 of our 5-day online FDP. Today, our session will be on GIS in urban sprawling, taken by Dr. Prasija AV, Associate Professor, SCMS Ernakulam. Now, I kindly request HOD Civil Department, Dr. Alvin Verghese, to introduce the speaker to our audience.
Good afternoon, all. Good afternoon, honored guests, esteemed principal, colleagues, and participants. It's my pleasure to invite you the faculty development program on innovations in civil engineering, integrating geospatial technologies, structural monitoring, AI, and sustainability on second day. We truly honored to have Dr. Prasija AV, Associate Professor in Department of Civil Engineering at SCMS School of Engineering and Technology, as a distinguished speaker for today's session of this FDP. For Dr. Prasija AV received her bachelor degree in civil engineering from TKM College of Engineering, Kollam in 2004. She earned her MTech in geotechnical engineering from IES College of Engineering, University of Calicut in 2012, and her PhD in water resources engineering from GEC Thrissur in 2021. With nearly a decade of experience in GIS and remote sensing applications for groundwater studies, Dr. Prasija's work focuses on groundwater contaminations, groundwater modeling, the application of natural fibers as a remedial measures against contaminations, soil erosion modeling, and related topics. Also, she works a lot. She is an active researcher with numerous national and international publications in these areas, and he is currently involved in various consultancy projects related to GIS. Currently, Dr. Prasija AV is serving as a principal investigator for K2 Research Seed Mandi project titled Study of Dispersity Coefficient of Contaminants through Different Types of Soils. We look forward to gaining valuable knowledge and insight from her expertise during this FDP. Thank you. Thank you all. Welcome, Dr. Prasija AV.
Okay, thank you, sir. Am I audible?
Yeah, it's audible.
Yes, ma'am.
Okay, first of all, I thank the coordinators of this program for inviting me as a speaker for this session. Okay, then let us start, right? Okay, let me
Yes,
share
ma'am.
the screen.
It's clear.
Participants are joining, but we can start.
Okay,
So almost 70 participants already joined.
okay.
70 plus. And some participants joined in the YouTube too. So
Okay, fine, sir.
it's totally 100% participants presently joined here.
Okay, fine, sir. We can start. Let me share my
Yeah.
screen. Okay.
Okay.
Screen visible?
Yeah, it's visible, but it's not full screen.
Okay, sir. Okay. It's
Yeah,
okay,
now
right?
it's okay. It's okay. It's okay. Yeah, it's changing. Correct.
Then we can start, right?
Okay.
So once again, good afternoon to all the participants present over here. Myself, Dr. Prasija, and today I am going to present the topic on GIS in urban sprawl. So, as we all know, this urbanization is not a new thing, right? So, this urbanization is actually a universal phenomenon that happens all over the world where human dwells. And this may be due to, the urbanization is due to mainly reasons like population growth, increase in economy, then what infrastructure development, industrial growth, etc., etc. And all countries and all regions are actually prone to this phenomenon. And actually, it is an inevitable thing. Urban should grow and urbanization should take place. But why this matter? Why this topic is actually a matter of concern nowadays, and how it become an environmental problem, or how it become an environmental crisis nowadays. So, what is the need of studying this urban sprawling, and what are the various methods of studying? And after studying, what are the outcomes that we can gain from such a study? So, these are the things I would like to brief out in this session. So let us see one by one. So now we can see what is this sprawl actually means. The sprawl is a term that is often used to describe perceived inefficiencies of development. That means it is actually the sprawl can be happened when the urban growth is not in a proportional way of the normal trend line. So the urban planners has already set one trend line for a particular urban area, like this should be the growth trend line for the next 10 years, and this should be the growth pattern for the next decade. So if this growth doesn't happen in that proportionate way, then we can say like the sprawl has happened. Okay, so in developing countries like India, where the population is over 1 billion, urban sprawl is taking its toll on natural resources, because when urban sprawl happens naturally, it will affect the natural resources availability. So it will continuously on reducing or alarming pace. That is the cause of what is the effect of urban sprawl. So now we can see what is the major difference between growth and sprawl. Actually, growth is something to be happened, and how it become a sprawl. So from this graph, actually can be seen like in the graph, actually the x-axis represents distance from center. Of the readable, I will tell. The x-axis represents distance from center, and y-axis represents some sort of density. The density can be like population density, it can be like built-up ratio, anything. Okay, some density is shown in the y-axis, and the x-axis distance from center is shown. And here, one black line you can see. This is what the city before change. That is when a city has developed, how the growth pattern should be. The urban planners has suggested some trend line. That trend line is shown as the black line. Okay, and distance from center in the x-axis means now it is here in the y-axis. The x-axis 1. 1 means something or 1 kilometer or 1 mile from the center of the city. 2 represents like 2 kilometers from the center of the city. In such a way, we can identify like these regions are like urban areas, and to the extreme, we can say it is like rural areas. So in that way, you have to observe this trend line, that black line. So the growth should be in such a way that the urban planners have suggested. So if we can, if the study has evolved, and if we plotted some urban growth after 10 years, if the trend line shows like this blue line, if the urban growth has a pattern show like as it is indicated in blue line, it can be say that urban growth has happened. Why? Because it follows the parallelism of what the trend line has fixed by the urban planners. So the growth has happened in such a way that it is proportionate to what it has suggested in the the development stage of the city itself. But if the growth is like this red dotted line, we should say the growth leads to sprawl, because what? There is a density gradient that tends to slope downwards away from the city center, because it happens actually due to what? Improper planning, or maybe due to the migration of people from nowadays. It is seen like people are migrating from more from urban areas to rural areas for getting more harmony in living conditions with the nature. They are moving more towards the rural areas. This may also due to the reason why this density gradient has happened. And while moving to rural areas, what happened is like already the rural areas has some basic amenities or basic facilities for that particular population. And if more people get migrated from urban to rural, what happens is like the shortage of facilities, for example, like water, sanitation, electricity, everything will affect, and it will lead to more complications. So this is what this urban sprawl refers to. Like if the growth is uncontrolled or without proper planning, that is, if it causes any complication, then the growth can be said like sprawl. Okay, so every time the growth is not a sprawl, so if it is not coming in a proportionate way, we can say like sprawl has happened. So a study is actually inevitable to identify whether the urbanization happened in a proportionate way or in a disproportionate way. So that is a necessity of the study. So why come is like making cities sustainable. So what is the need of studying this urban sprawl? Like we all need sustainable cities. So for making the sustainable city, the urban planners should know the urban morphology, population estimation, and other physical aspect of urban environment. So and for reducing environmental impact as I explained, like while migration of people takes place from urban to rural areas, obviously the environmental impact on facilities may happen. That is updating and monitoring environmental changes we need. For that, we have to study urban sprawl. Site suitability we have to check for, and catchment area analysis also we need to check for. These are things we can do by studying this urban sprawl pattern. And for creating equitable and healthy communities, that is where all the slum populations are there, and for monitoring and updating these all things, we need this urban sprawl study. And for urban planners, actually, it requires information to provide basic amenities such as water, sanitation, electricity, etc. There, they need to identify like everything is happening in a more comfortable way, or any complications are going to happen. So for all these things, we need to study, or we need to look into for this urban sprawl things. So these are some of the methods or the types of urban sprawl. Not the type of urban sprawl, is actually type of growth. Okay. And every growth, if it is not in a proportionate way only, it leads to sprawl. So these are some of the types of urban growth actually. So first one is linear growth. Linear growth, as we can see from the figure itself, we can identify like the growth has happened along the transportation facilities. For example, the growth has can be along the way of highways, or along rail lines, or along water bodies. Any navigation systems are there. If the growth has happened along coastal lines, it can be say like the linear growth. And all these types have its own advantages and disadvantages. Like for linear growth, actually it is easy to provide infrastructure in a single axis. For urban planners, it is easy to provide along a single axis. But the disadvantage is like it will actually keep aside more spaces beyond this lines, beyond these parallel lines. There may be some open spaces can be leave. That's the disadvantage of this linear growth. And cluster growth is like some form of clusters have been, compact clusters have been developed by such growing patterns like industrial growth, or any infrastructure, or flat developments. The some sort of cluster has happened. It is called cluster growth. It also leaves some open spaces or green spaces in between. So it is an advantage is like it has enough green space or open space in between, much more population growth in between. Some few spaces are available. And disadvantage like it can face some transportation challenges. In the linear growth, actually the growth has happened along transportation facilities. In cluster growth, it is not actually taken. So the commuting facilities may affect in this cluster growth pattern. The leapfrog growth, actually, it is not of it is jumps over. It jumps over available land. Some available land is there, but it jumps over the available land, and some population or cluster growth has happened here and there. And actually, its advantage is like it can create future developments in nearby, like infill developments. Then land use changes can also be possible in this leapfrog pattern. But it can another advantage like it can temporarily reduce the cost of land also, because the growth has happened here and there. No one can say like this is a commercial land, so the rate can be increased in such type of growth. Okay, and here the disadvantage is like it is very inefficient infrastructure pattern, which can lead to improper traffic, and it can lead to environmental damage. Like online delivery problems, like that. This the growth is actually it's not a traditional way of urban growth. So these are some of the usually happened methods of urban growth, and these are the growth patterns. And if it leads to a disproportionate way, and if it goes in discomfortable, it will lead to sprawl. So now we can see what are the different methods of studying urban sprawl. So first of all, it is remote sensing and GIS. And remote sensing and GIS is the most inexpensive method for studying by using satellite images and we can use spatial data, survey data, etc. Can be incorporated in remote sensing and GIS, and is mostly the adoptable inexpensive method. And next method is like quantitative indices and statistical models are there. Actually, in remote sensing and GIS, what we are doing is like we are just getting a pattern analysis that we are doing in GIS, not much of quantitative values that we can't obtain. Some sort of percentages, obviously, we get, but how much sprawl has obtained, or how we can tell like this sprawl. In that way, the quantitative analysis is actually not possible by means of this remote sensing and GIS, so that we have to get help from this quantitative indices also. Okay. So in this presentation also, I would like to give you an example of how to map this sprawl pattern with remote sensing and few indices also. Okay. So these indices actually can be used together with this GIS modeling for get a quantitative analysis of this urban sprawl. And field surveys and ground truthing also, like surveys are usually taken, like how much populations are there in each and every home, and like ground truthing also. Like these all things are actually input to GIS and remote sensing also. These all data are actually required for getting more information on this growth on population. Next method is like urban simulation and modeling. Urban simulation is like a lot of numerical simulation models are now available, like urban sim, city engine, sleuth. In most of the papers, we can see the sleuth model. Then transims, it is especially for transportation analysis. And these models can actually predict, like by based on the historical data or input data we are giving. Based on that data, it can predict like after 10 years or 20 years, what will happen to this pattern of urbanization. In that way, it can prediction models are available. And socioeconomic and demographic analysis is actually by means of what census data, then economic reports, then surveys, field surveys, etc. Based on that, population studies are actually conducting in the socioeconomic and demographic analysis. So this urban sprawl can be identified by means of either analyzing the population growth or by analyzing what the physical developments, then or by analyzing how much agricultural land has reduced. In many ways, this urban sprawl can be studied. So the last method actually remains for how the population growth has taken place in an urbanization. In that way also, we can study the urban sprawl. So in this session, I'm going to deal with like the remote sensing and GIS, quantitative indices, and how this ground truthing is, what is the importance of ground truthing is also I would like to mention. Okay. So how this remote sensing actually, what is the application of remote sensing in this urban sprawl? So first of all, I would like to just go through the introduction of remote sensing, because most of the terms in remote sensing is actually much more important, while I am going to explain with the procedure using indices and all. So some basic terms I would like to refer here. So the principle behind remote sensing, we know the solar radiation is the major source. And from the solar radiation, the radiations are actually transmitting through the atmosphere, strikes on Earth's surface, and these radiations, based on which material it strikes, the radiations can be reflected, absorbed, or it can be transmitted through the surface. And this reflected radiations actually again transmitted to the atmosphere, and the sensor get captured this reflected radiations. And these reflected radiations are actually absorbed or captured by the sensor, and the sensor actually convert these radiations into usable information and useful satellite information. And this satellite information is again transmitted through atmosphere and reaches our ground monitoring stations. And from the ground monitoring station, the satellite data are processed, and it is get into digital or hard copy images, or transmission of recorded information into ground station for analysis of data. And this analysis part is our GIS portion, ground information system. And these all things are remote sensing. So remote sensing, actually, we could say like it is a data acquisition process. How the data of this Earth feature is getting into the sensor, and how it is converted into a satellite information to our ground monitoring station. These things are happened in the principle of remote sensing. So, and after that, the satellite images are transferred to analysis to GIS experts. Okay, and this is the principle behind remote sensing. And in the electromagnetic radiation is actually defined by means of electromagnetic spectrum. And the electromagnetic spectrum, from the school days itself, we come to hear this electromagnetic spectrum. That is, the wavelength of each radiation is actually measured, is given in the scale in micrometer. And here you can see gamma rays, that is a law. Shorter waves are gamma rays, X-rays, then some UV rays, visible light. Visible light is our VGOR, and here the wavelength is actually vary from 400 to 700 nanometer or 0.4 to 0.7 micrometer. That is the visible light spectrum. Then comes the near infrared, thermal infrared, then radar wave, and some gamma waves are also there. The radio waves and microwaves are there. And these are the electromagnetic spectrum. And in our study of remote sensing that is used for urban sprawling, actually we could identify like how the bands are fixed based on this electromagnetic spectrum values. That is the important thing. So in remote sensing, band refers to specific ranges of electromagnetic spectrum that sensors detect and report. Each band corresponds to a particular wavelength range, and different material reflect or absorb energy differently in each band. Thus, this visible light spectrum, actually in the Earth's surface, actually we are getting like visible light and some near infrared. These are the radiations actually strike on the Earth's surface and reflected back. And how much will be the reflection and which all features reflecting which all electromagnetic radiations? That is most important. So these are the, here the left side is indicated like visible light spectrum ranges from 400 to 700. Near infrared is 700 to 1100 nanometers. This unit is nanometer, and here is micrometer is given. So here comes the band details. So band 1, that is 0.43 to 0.45, and here you should identify like 0.4 to 0.7 is our visible spectrum. So 0.43 to 0.45 is band 1, and band 2 is 0.45 to 0.51. And the applications like these bands are actually reflected, or these bands are important for identifying coastal water aerosols, band 1. Band 2 is for bathymetry and vegetations. Vegetations means minor or minor vegetations. Band 3 is for plant health and urban monitoring. Band 4, 0.64 to 0.67, that is for soil, roads, then barren land or infrastructures, extra for band 4. And band 5, vegetation biomass. So these all are the band definitions, and from 0.4 to around, that is band 1 to band 4 is, now we can see like it represents the visible spectrum. And near infrared spectrum comes to 0.85 to 0.88 is used for identifying vegetations. And SWIR means shorter wave infrared. It's also infrared, but short wave infrared is band 6 and band 7. This is useful for detecting moisture, soil, snow, minerals, etc. Okay, so so this is one of the important spectral reflectance curve. It is very important to identify how much each features on the Earth's surface reflect these radiations. It is a standard curve. It is not a result of a particular study. It is a standard curve in the remote sensing, like how the vegetations, how dry bare soil, or how water reflecting these electromagnetic radiations. So in this figure, we can identify like this black bold line represents the spectral reflectance curve of vegetation. And this dotted line indicates the reflectance curve of dry bare soil. And the dotted line in this visible region, some small heap is shown here. It is the reflectance curve of water. And from this reflectance curve, we could identify like all the, if there is a water body, if some band of light gets strike on a water body, only the visible light is getting reflecting. The y-axis is reflectance. So only the visible light spectrum is reflecting from the water body. all the near infrared and shortwave infrared are getting absorbed by the water bodies so that no reflections will take in place and nothing will be captured in the sensor or satellite images. So it is very important that if we want to study about some water bodies, what happened to water bodies in the past 10 years, if we could identify like that, we could go for this near infrared spectrum. Why? Because if the satellite image corresponding to this band, that is near infrared, that's band 6 and band 7, if we are observing that band spectrum of satellite image, if we can see some dark patches or black patches on that satellite image, that means that is a water body because nothing is reflecting. Nothing is NIR and SWR is completely absorbing and no radiations are actually reflecting from that particular area. That means that particular area is water body. So this is that is the importance of this spectral reflectance curve. And now we can see like vegetation strongly reflecting NIR. Near infrared radiations are much more effective for vegetation. If the spectral reflectance curve is around, the reflectance show is around more than 40%, that means that particular feature is a vegetation. Because the satellite image is as like black and white, nothing we can identify from a satellite image. It's as like an X-ray pattern or like a black and white fumes or like that. Okay. So if we are doing the process, the image processing, the reflectance value will come like it is above 40% in near infrared, we could identify like that feature belongs to vegetation. And if this SWIR range for vegetation is also along 30%. And for the bare soil, the soil also we could have different spectral reflectance patterns for different type of soil like clay soil, sandy soil, because clay soil have much more water content. So the near infrared, in the near infrared section, the clay soil will show less reflectance. While the sandy soil will show more reflectance. So in that way, different types of soil can also be identified by means of spectral reflectance curve. This is actually an average of, I am just showing here, just an average of all the features. Actually, we have different spectral reflectance curve for different things. For bare soil, soil itself has a reflectance curve, which will show different types of soil. Vegetation itself has a reflectance curve where it will show like deciduous forest will be like that, coniferous forest will be like that, thick forest will be like that, shrubs and herbs, how it will be. And in that way, the spectral reflectance curve are actually described. And the built-up areas reflect more in red and SWR. This is important for us to understand for this session because in some more indices will be explained later. In that indices, some equations will be there, and this equations is based on what band is actually useful for a particular feature. Like built-up area is actually reflecting more red than SWR, so that band is actually important for marking built-up areas. So that is the role of remote sensing in urban sprawl. Like high resolution images help classify urban and non-urban areas. We can while we are downloading satellite images from a particular site, we can see like many resolutions are available, like low resolution, medium resolution, high resolution. So it depends upon our what our intention of the work. It is like doing a UG project or PG project or a departmental work or for some governmental work. We need to choose like which type of resolution images we have to collect for. So this type of images are available in our website, and it is useful for classifying this urban and non-urban area. And time series data of satellite imagery captures broad progression at regular intervals. Time series data means if we are entering into a particular website, we can specify date. Like for my study, if I need a 10 years data of Ernakulam district or Thrissur district, if I need such data, I can specify the date, like from January 1st, 2000 to from January 1st, 2025 are required. In that way, we can mention the date. So the time series data of satellite imagery is also available. And remote sensing provides environmental data, that is like vegetation index, elevation, water bodies. That is, it can actually give remote sensing data. From the satellite data, we can get all the indices. Then at the same time, elevation patterns also in the form of DEM, that is digital elevation model. From there, we can identify the topographic patterns of each location, and we can identify water bodies. And historical imagery helps understand past trends. Like that, if we are downloading the images of 10 years back, we can just identify like how the land use has changed from the past 10 years. So these are the role of remote sensing in urban sprawl. And now we can see what is the role of GIS in urban sprawling. So how the satellite images are capturing and how it can be used for urban sprawl, that we can see in remote sensing session. And we can see how the analysis, because remote sensing and GIS together form a particular system, and particular system for studying this phenomenon. So in GIS, we have two types of spatial data. One data is called actually vector model, and another one is raster model. So GIS is actually a mapping tool, and for doing any spatial geospatial analysis, we have to go for this GIS platform. And GIS platform support two types of data like vector model and raster model. In vector model, all the features are classified into three, like points, lines, and areas. So here in this picture, in the right side picture, it is shown. The bottom picture shows the real world where we can see vegetations, water bodies, infrastructures, everything is there. How it is actually modeled, or how the data can be represented by means of vector model is giving the top two layers. That is, some houses are there. In the real world picture, some houses or individual homes are there. That's plotted by means of points. And some roads, streams, river bodies are there. That is actually plotted by means of lines. And some vegetations or forest areas, that is by means of these polygons. So in that way, vector data model is represented in GIS. And raster data model is represented by means of simple images like pixels. Pixels are the unit of raster data model. That is, here it is shown the elevation details. Topographic details are shown by raster model. That is by means of a pixel. But while we are taking a photography by using our camera itself, while we are zooming out, you can see small pixels in your image. That is actually a raster data. So these vector models are actually used for distinguishing or representing discrete features. Discrete features means that is it has some proper boundary. Discrete features are better represented by means of vector model, and continuous features are better represented by means of raster model. Continuous features, for example, like temperature, elevation, precipitation, these are continuous data that we can't represent by means of a boundary or by means of specific polygons, lines, or all. These all details are better represented by means of raster model. So how the satellite image can be classified, satellite image, whether it is vector model or raster model. Because if we are downloading satellite images for processing, we have to import these satellite models to the GIS platform. So while importing, in which method we have to import? Is it a vector or raster model? If it should be a vector model, then it has to be represented by means of lines, polygons, and points. So the satellite image, why we are importing by the method of raster importing, because it is just an image. Okay, and after importing, we can convert it into vector model. That is another use of GIS platform. Like all the vector model can be transformed to raster model, and raster data can be transformed to vector model. These two things are possible, depends on our purpose. So this is a vague idea of what the GIS happens. And some data analysis tools also you should familiar with this process. And in the vector data analysis, basically, there are so many analysis patterns are there. Basically, there are three things like buffering. Any disturbances in between? Okay. Okay, fine. So these are some of the vector data analysis that is available in GIS software. First one is like buffering. Buffering, the term we are very familiar with, what is buffer zone and all. So using buffering, we could in the urban sprawl, on the focus of urban sprawl, I will define buffering. So in the case of urban sprawl, we can identify like how much urban growth has happened along a particular water body or along a transportation facility roads. how much urban growth has happened 5 kilometers away from this national highway. In that way, if we want to do analysis, we can go for this buffering zone. And overlays like we can overlay any number of layers can be overlaid in the GIS platform, and you could analyze the growth patterns. I will show you this buffering details. Okay, these are the examples of buffering. If we want to buffer like 2 kilometers away from national highway, how much growth has happened? We can just give the input value. We can just select the feature of that particular road, and we can, if we give the value like 2 kilometers or 5 kilometers, it will clearly show the boundary. And if we want to get buffering a point, if you are selecting a particular industry, and you could identify like how much growth has happened around 10 kilometers around the industry, you can go for this circular type of buffering. That is the example shown on the right side. Like we can clearly identify in that much area how much built up area has come in the past 10 years. In that way also we could identify. That's the use of this buffering tool. And this overlay tool is like I already told, like the vector data is of 3 types: points, lines, and polygons. And we can overlay these layers, like we can overlay point over polygon, we can overlay line over polygon, and we can overlay polygon over polygon. And here I am just showing the example of polygon over polygon. And this is layer 1 of geographic data. It consists of some information. And this attribute data is also a feature ability of GIS platform. Like for every feature, we can save some informations also. For example, for national highway, we have informations like where to where this road is connecting, how much width is that road. And so many details are there for these highways. So if we have to add some informations regarding a particular feature, that's an option in the GIS platform that we can, like an Excel sheet, we can add features by means of geographic coordinates. We have to input like longitude and latitude of particular feature, and we can add any number of informations in the attribute data. So here this attribute data is shown for this particular layer. And for layer 2 also some attribute data is given. And if we are overlaying these two data, the output layer will show all these informations. That is the another feature of GIS platform. Like if we are overlaying any number of layers of data, the output layer will show all the informations of the layers that we have overlaid. So the attribute data table gets enhanced, and it shows class and post at the same time. That is the output. At the same time, you can retrieve the original data also. That is the overlay method. And now comes the raster data analysis. Raster data analysis is like is just an image, right? The unit is like pixels. So here we can do so many mathematical operations. So in the vector data also, while we are overlaying, we can go for any analysis, like any mathematical analysis, like we can that Boolean logic also we can do, like and option or option. We can do union, then intersect. Some mathematical functions are there. No, that things are we can do in this overlay procedure. The same way in the raster data analysis also, all the mathematical things can be that we can do, like addition, subtraction, averaging, then logical operations, logarithmic operations, trigonometric operations. Everything can be do by in the mathematical operations of raster data. So here it is shown like some addition. One layer is overlaid over another layer. The logical operations, if we are giving like addition, the output layer will show the addition of pixel numbers. Here, everything happens by means of pixel values. If you are giving mathematical operation as addition, those corresponding pixel will get added to the resultant image. The focal operation, if we are giving the summation or averaging, we are giving like some code like neighborhood of 4 values should get averaged, and the output value will give the corresponding pixel value. The zonal operations, like some zone patterns are given and some values are also assigned. For a particular zone, what is the averaging of that value? In that way, actually, the raster operations are happening. And the raster data analysis, we have another option like raster calculator is also there. In the raster calculator, we can do all the equations. We can just type on all the equations The equations, the inputs are like the satellite images, and we can do any sort of operations in the raster data. This is a brief overview of what is happening in the raster data analysis tool in GIS. Okay. So other raster data operations involves, these are all applicable for vector data also. The basic important terms like clip and mosaicing. Clipping is like, here you can see one example. Suppose this is my shapefile or the study area boundary. If I am going to study about something about Thrissur district, suppose this is a Thrissur district boundary layer, and I got a satellite image covering at another region also, like a square image I have obtained at somewhere is the Thrissur area. Okay, so if I want to click this correct the information on Thrissur district itself, I can go for the option clipping, so that I can add this layer over this layer, and if I'm performed by means of clipping tool, the resultant will be like this. The shape is actually overlaid. Shapefile is overlaid over this particular satellite images, and the resultant images will show the information on that particular shapefile. This is the option called clipping. At the same time, mosaicing also very useful for this urban sprawl study. Mosaicing means while we are downloading satellite images from various websites, in some website actually we could clearly choose all the if we are studying for Ernakulam district, if we can select Ernakulam district as a whole, as one satellite image, as like this one satellite image that we can obtain, so that we can clipping it the Ernakulam district over from here. In some cases, in the site like Bhuvan or NASA ISRO website, so many tiles of data we are obtaining, not as a single satellite image, so many tiles. That is maybe 10 or 20 tiles, if we are clubbed together, only will form like Ernakulam district. So this type of tiles of images, if we are obtaining, we have to go for the option mosaicing. And the mosaicing will lead to a single image. So we have to select all these images and click for mosaicing, and we will get a mosaic image. And then we have to go for this clipping for getting the Ernakulam district shapefile. Shapefile has to overlay over this satellite data, and we have to clip it for. So these are some of the data operations that can be do in both vector layer and raster layer. So this role of GIS in urban sprawl is like, it is possible to spatial modeling and pattern recognition technique. It can be used for spatio-temporal analysis, and so it can track the speed and direction of urban expansion. So while we are importing so many satellite images, maybe the 10 years data or 20 years data, we can clearly identify like what was the growth pattern 10 years before and what was the growth pattern in the current scenario. That way of spatio-temporal analysis is possible in the GIS platform. And it integrates demographic, infrastructure, transportation, and environmental data for the comprehensive planning. Actually, in the GIS, not only the satellite data, many forms of data can be imported to the GIS. Like in the methods of urban sprawl, we have mentioned like field survey, ground truthing, population data, etc., etc. If the field survey is one, if we are getting a data of field survey in the form of Excel sheet, that data can also be imported to GIS. Not only the satellite data, any data can be imported. In the Excel sheet, only the mandatory thing is like, for every feature, there should be, its coordinate system should be defined, like geographic coordinate system, like longitude and latitude should be defined for clearly for each feature, so that we can import Excel file, we can import notepad details. Then we can import, if we are using some total stations and all, we can directly import the data from total station to GIS. So all the data can be actually integrated with the GIS platform. And some models also specified in the methods like SLUIS, ANN, then urban plan. In that model also, actually for getting the real field scenario, the result from the GIS has to give the input for such model. So these models also need GIS output as their inputs. So they are used to simulate. Then that model will be working for simulating future urban growth scenarios. So these are the role of GIS in urban sprawl. So these are some of the examples I just got from some journals. So here it is shown like what happened for a particular city. The radial way of growth pattern is shown from 1973 to 2010, how this urban growth has happened in a particular city. Here also we can see this urban is shown by this red color, and other things, urban and other things is also plotted here. Then water bodies is blue. Okay, so this how this urban pattern has developed in the from 1973 to 2010, and land use changes can also be studied by means of this combination of RS, remote sensing, and GIS. That is, land use, land cover pattern study can be done by means of this GIS. So here you can see like vegetations and non-vegetation areas are actually shown from 1973 to 2009. How much percentage of area, vegetation area was there in each area, and how much area is given in hectare. And here also built up area, vegetations, water bodies, and others are given in different colors. So you can see the patterns. Actually, the spatial pattern is actually visible by means of this remote sensing and GIS. And here also another example like urban sprawl mapping, that is from IIRS. Here also map of Gurgaon city is shown from 1993 to 2005, how this urban sprawl has happened. So now we can move on to what's the methodology, how we can do this urban sprawl study by means of these indices and this remote sensing technology. So first thing, we have to collect satellite images from any site, and we have to do some digital image process. So while we are obtaining satellite images, it won't be much clear. So we have to go for some digital image processing. I will show you some tools that we can use for digital image processing. And we have to go for some classification methods. Then after classification, we can go for accuracy assessment. Then we can do the land use, land cover mapping, and we can click the built up area. Okay, so these are the methods we are going to cover. So I will just show you with an example of Ernakulam district. So this is the study area taken for studying the urban sprawl from the past 10 years, like from 2013 to 2023 is the time taken for studying this urban sprawl. So Ernakulam district is the example that I am going to show here. So we have various satellite imagery data sources from USGS. We can download, then Sentinel, NASA, NOAA. From for all these satellite image platform, we have to get some registered login ID, and using that login ID, we can just given the source, or we can type where which location we need that satellite images. That location we have to specify there, and after that, it will ask like in many most of the websites the detailing is actually different. In some of the website, it will ask like temporal data we need, or spatial data, or temperature data, and we can specify bands also. Okay, it's different from website to website. So I will just show you the USGS platform, just a screenshot of USGS platform. So in USGS platform, we can, if I type Kerala in the location, it will zoom out the area of Kerala, and we can specifically select the Ernakulam district. Ernakulam district, we can't do like the boundary of Ernakulam district as like we can't get. We will get a square area. That is, we have to select a polygon over here. We have to draw a polygon over here. That means we have to get satellite image of that much area. In that way, we have to select, and we have to specify for which all band we require for a particular type of study. And based on that, bands can be collected. So here, Landsat 8 band 456 of the date 13/4/2030, and Landsat 8 band 456 of 2023 has taken. So in that way, by specifying the year, we can collect the data. And by collecting the data, for comparing data of two different years, we should make clear that the data entered for acquiring data should be same. Otherwise, the comparison may not be possible, because so many options are like cloud coverage, then sun corrections, then temperature corrections. So many terms are there. So what all things we are collected for a particular year, that feature should be applicable for the next year also, so that we get the satellite images correspondingly. So these are the resolutions, different type of resolutions available in most of the sites, like low resolution, medium resolution, and high resolution. So depends on our work. For which type of work we are doing, we can opt for that type of resolution. I think for high resolution images, we need to, in some site, we need to pay for. And in USGS website, actually, not in USGS, NASA website, actually last year when we are downloading a few satellite tiles, that is more number of tiles we required for plotting one district. So when we are downloading that number of tiles, it is given like for a single user, only 20 tiles are allowed to download in a single day. In that way, restrictions are there in few sites, and some resolutions also may be restricted. So depends on our work, we can select. The resolution actually is a raster data feature. That is, if I am mentioning like spatial resolution of 5 meter, that represents each pixel in that particular image covers 5 meter in the ground. That is the meaning. So here what it is, it's low resolution, that is 360 meter. 360 meter represents what? 1 pixel in that image represents 360 meter in the ground. That is the meaning. So we can assume 1 pixel contains 360 meter details, means it has very low resolution. Okay, but it can cover more number of data, but the resolution will be less. And here the high resolution 5 meter means each pixel in that particular image covers 5 meter in the ground. That means it is with much more resolution. So it depends on our nature of work, we can select which resolution of image we require. So again, the band we have seen in the previous slide also. And here it is, I would like to show here. We can find options like which satellite image we have to download, like Landsat 7 or Landsat 8. And if we are selecting Landsat 7, some band value differences are there. Like band 1 is 30 meter blue in Landsat 7. At the same time, is band 2 for Landsat 8. So for which satellite data we are actually downloading depends on that our equations will get varied. While coming to this indices calculations, we require these band values. So it should be take care while downloading which satellite images we are importing. Based on that, the satellite images we have to put into the GIS. These band values are some sort of differences are there. So this is a step of digital image processing. So while downloading satellite images from a particular website, it won't be much more clear. Like we know the sensors are placed in satellites, and the satellites are moving at the same time Earth is also rotating. So the images are capturing while this movement is taking place. The satellites are moving in the anti-clockwise directions, and Earth is rotating in another direction. In that way, the images are capturing, so obviously some sort of geometrical distortions will be there. So in order to rectify those geometrical rectification, we have to done for geometric correction, and we have to go for radiometric corrections. And if we have some disturbances in the image, like sometimes it is blurred or images will not be clear, we have to go for this noise removal. And after that, we have to go for image enhancement. That is, each feature has to clearly distinguishable from another feature. In that way, the satellite images has to be processed. So that method is called this digital image processing. So these are some of the steps I have just mentioned here. First one is geometric distortions. These are the usual distortions that can happen while the satellite images are capturing by sensor, like earth rotation, altitude variation, pitch variations, then velocity, roll variations, etc. is actually expectable while capturing a image. So these distortions are actually affected in our satellite images also. So how it can be identified, whether it is distorted or not, while we are importing those data into our GIS platform, it won't get matched to our actual site. it can be seen like it is some distortions are there, or it is landing or not correctly matched with our geographic coordinates, and we can rectify that. Actually, sometimes it may be the recorded data, and actually we need like the data will be like this. So how it can be possible to correctly importing those data into our GIS platform is like we can do georeferencing. The process is called georeferencing. We can import those images into our platform, and we can correctly, if we know some ground truthing values, that is, if we can clearly identify, like here some infrastructure is there, and if we know the correct longitude and latitude values of that particular position, we can input those values and we can do the corrections. And in that way, we can clearly rectify those distortions. And that process is called georeferencing. And this radiometric corrections is actually, it indicates like some sun angle correction. That is, we know like the position of sun is actually varying in each season. Summer season, it will be like the position is here. Spring season, the position is here. Winter season here. In the same location. For the same location, the sensor capture images in these 3 seasons will be different. So while we are collecting those images, sometimes the image will be like this. So we have to go for that particular correction also. Actually, the GIS platform, actually we have to just click on digital image processing toolboxes are available. In the toolboxes, we can just click on the image and just click on the menu like sun angle correction should be done. It will be clear. The procedure is actually very simple. These are one of the another step in digital image processing. And noise removal, we have many methods for noise removal. Like here you can see some strips of line strips are seen in satellite image. This line strip means each strip has some missing pixel data value. And those missing pixel data value can be incorporated by means of averaging of pixels. That is, methods are available. Like we can average, we can just fill that pixel value with the averaging of nearby pixel values. So how much pixel value has to be averaged? In that way also we can direct like 3x3 windows or 4x4 windows, 5x4 windows, and we can just select that particular window and just we can rub over it. By rubbing over this particular image by 4x4 window or 5x5 window, it will average for a neighborhood 5 pixels and input those missing pixel values with those average values. In that way, we can correct or we can rectify many distortions or many noises in this digital image processing. And this is what image enhancement. Here the features are actually not distinguishable from one another. And by using this image enhancement toolboxes, various toolboxes are available, like we can check for contrast, then brightness, then we can, then manipulations tools are there. And in that way, we can use a proper tool for enhancing the image. So these are some of the methods that we can do for digital image processing. Actually, this step is also not mandatory, depends upon our project. Like if we are doing for a UG level project, this step we can skip for, because the processing is actually a tedious procedure while doing it. So we can directly import that satellite images and go for the next. So it is not a mandatory step for some sort of. And the process satellite images can be actually imported, and we can make the correct geographic coordinate system for that particular image. And the output of that particular image after correcting the geographic coordinate is called georeference image. So this is the shapefile or shapefile with georeference data. Now we can go for the index calculations. How we can go for this built-up index. So mainly we have 3 indices: NDBI, NDVI, and built-up index. That is, NDBI is normalized difference built-up index, and it is normalized difference vegetation index, and built-up index is BVI. So built-up index is a remote sensing derived index used to quantify and map the extent of built-up areas. It is often derived from combination of spectral band. So that's why we have defined band in the previous slide. So by analyzing this BUI over time, we can measure spatial expansion, how the growth has expanded over a particular year. These things we can just analyze by means of this built-up index. And this built-up index is actually useful for plotting this LULC classification also. And this is what the normalized difference built-up index NDBI. So for NDBI, the highlight the presence of man-made structures and impervious structures. Only the built-up features are shown in this index. Its value can range from -1 to 1. So negative value shows non-built-up areas, natural features like vegetation and water body, it indicates, and positive value indicates high proportion of built-up surface. So this is the equation for NDBI. SWIR, that is short wave infrared minus near infrared, divided by the addition of these two. For Landsat 8 data, this SWIR corresponding to band 6, NIR corresponding to band 5. So here comes the application of band details. So how we can perform these equations and all? Actually, while we are importing this satellite data into our GIS platform by means of raster import, after importing this raster data, we can go for the option raster calculator. In that raster calculator, we can see how many number of images that we are imported into that GIS platform. So by clicking on that particular, so for example, if I am downloaded like band 6, band 5, band 3, and band 4 at the same time. But for my equation, I required only band 6 and band 5. So by opening that raster calculator, I can select which satellite images has to go for this equation. And I simply select on band 6, then put minus sign, then select band 5, then close the bracket, then put the division symbol, then again click band 6. Then we can write the equation over raster calculator. For our duty or for performing this analysis in GIS, actually we require only this much idea, what is the equation and how it can be selected. Rest other procedures will be done in the software itself. So these calculations will be done in the raster calculator for built-up index. In the same way, vegetation index we require band 5 and band 4. That is near infrared and a red band is required. So this equation is the same pattern we can do in the raster calculator. Here, it measures the density and health of vegetation. Higher NDVI value represents healthier vegetation and lower value indicates non-vegetated surfaces. And what is built-up index is like the difference between these two, NDBI minus NDVI. So after processing this NDBI and NDVI, we will get output images like NDBI of 2013, NDBI of 2023. At the same time, NDVI of 2013 and 23. What about the temporal variations that we are going to check? In that way, we have to rename that particular satellite output images also. So after that, again go for this raster calculator. We can again select that output NDBI of each particular year and go for this process built-up index. So this thing actually I have already explained. So this is a raster calculator. Here you can see how these equations are typed in raster calculator. Like band 5, actually we have to rename the satellite images. Like otherwise it will be misinterpreted or actually the mistake will happen. Like selecting the satellite images, because while we are downloading the satellite images, the name is like such a lengthier name. We can't identify like which represent band 5. That much lengthier name is there. So we have to rename like it represents band 5. Once we are downloading a single satellite image, at the same time we have to rename like it is band 5. It's band 4. Otherwise it will get mistaken in the GIS platform. So in that way we have to write these equations in the raster calculator and perform. This is one another application that we can do in raster calculator. Like we can masking over. If I want to see a particular area having NDVI greater than 30%. If I want to see that particular area itself, I can give this type of command like NDVI greater than 0.3. So in that particular image, it will result in another image which shows only the regions where NDVI greater than 0.3. In that way of analysis is possible in raster calculator. In our normal performance of another work, like if we are giving for population data in a Ernakulam municipality, if we are assigning some population data, that is Ernakulam district we will see as like a polygon data, and population data will be like a point data. And in the raster calculator itself, we can give like, I have to see in some taluk where the population is greater than 10,000. So it will clearly indicate that region where the population is higher than this particular value. This is also possible in raster calculator. So these are the results that obtained after NDBI raster calculation. This is the image obtained. Actually, the image obtained is like black and white color, and we have to do the corrections. We can do the coloring techniques also, coloring methods also available in GIS, like which color has to indicate for vegetations and which is for built up areas. In that way, we can select those colors, and otherwise we can't identify. So based on the legend we are giving, the values will be like this. And this and here this is the Ernakulam district for 2013 and 2013, and this is the calculation of NDBI. And here the value of high built up area density is actually more in 2023 from the images, and no regions have shown very high built up area. Only the medium level of built up area density is visible in 2023 data. Actually, the patterns we can't identify from here. We can just check over the values like -1 to 0.76 low built up area, -0.76 to 0.168 medium built up area density. These are the standard values given for NDBI. So based on that, we could identify like how much density of built up area is happened in 2013 and 2023. Like that, vegetation index result is like this. So based on that, 0.1 or less shows barren areas of rock, 0.2 to 0.5 sparse vegetations, and 0.6 to 0.9 dense vegetations. And based on that, we can assess like how much pattern has changed over the years. So these are the steps for index calculations. And now we can move on to how these land use land cover mapping can be done. For that also, we are actually downloading all the satellite images from the website. And these data sets were imported into LULC. Actually, what is the use of LULC is like, it can be, it's a crucial tool for various field of understanding how the land is utilized for different purposes and what covers the surface in a particular given area. For identifying such type of study, we have to go for this LULC changes. And for that, one tool is used in QGIS. It is called semi-automatic classification plugin. Actually, the QGIS software at another advantage is like, if we want to perform a particular analysis, if it is not available in our app or QGIS application, we can select it from plugins. Various plugins are available inside QGIS. And if we are connecting to the website, we can install that particular plugin and do the analysis. So here, SCP plugin is used for doing the LULC mapping. So for LULC mapping, the major thing that we have to go for is like classification methods. We can go for two type of classification. One is supervised classification, and another one is unsupervised classification. From the name itself, we could identify what is supervised classification. Like here, one person is supervising for a particular classification. So here, actually, we have to, the supervised classification, we have to assign various training fields. Training field means, yet another image. That image is missing. Training classification means we can assign as like, if for a particular satellite image, we could identify like, after doing this built up indexes and all, we can assign like this color corresponds to water bodies. So we can select that particular pixel and we can rename it like it is water. It has to be given blue color. And we are selecting yet another feature. If we know personally like that area is forest or vegetation, if we can select that particular area and we can mark like it is vegetation and put green color. In that way, we can train this satellite images. Because in the after obtaining this built up indexes and all, we can't identify like which is vegetation, which is urban area or which is built up area. Nothing is actually interpreted from that particular image. For getting more land use pattern, we can actually go for this classification method. So here we can training as like this feature corresponding to green color. So after assigning these all, after training these all set of data, the software will perform in such a way that wherever these colors are available, it will input those values to those pixels. So the output image will be much more pleasing. In that way, we can clearly identify which feature is available in particular location. So in the unsupervised classification is like we are not training here, but at the same time, some default methods are available so that we are just clicking on like which all data we have to see. Like we are just clicking on barren land, vegetation, and built-up area, and we are not selecting any features and inputting some color. So based on the trading that is defaultly programmed inside the software, based on that, it will give a classification. So it is actually a faster method. Unsupervised classification is a faster method, but not much accurate. But supervised classification is an accurate method. So we can go for both these methods. It also depends on the nature of work we are doing. So this is the step involved in land use, land cover classification. So this for this creation of LULC map, actually band 1 to band 7 of Landsat 8 has been downloaded from this USGS, and it has performed image processing, and this semi-automatic classification plugin has been used. And for this the supervised classification methods, we have to assign some values. It can input like RGB represents for which all type of band. That depends on Landsat 8 or Landsat 7, the value will be changed. So, and we can create any number of polygons. And here in this study, we have used actually 5 LULC classes like wasteland, water bodies, forest, built-up areas, and agricultural land. So this was the result of how this Ernakulam district land cover in 2013. So based on the training set we have given. So by selecting some particular point, if we could assign the value like it is a built-up area, it should be in red color. In that way, we have to assign those particular feature in the classification method. And this is the output of what we are obtained from for LULC 2013. And here the LULC 2023. Actually, these results are actually I obtained from UG project result. So digital image processing has not been taken place in this particular image. So this is just not an accurate result that I am showing. Just I am showing the method. So here you can see the built-up area, how much it has been changed from 2013 to 2023. So if we have done correctly the digital image processing and ground truthing purpose, ground truthing method actually it is like okay, I will come to that slide. And after doing this, we can check for accuracy assessment. It is also not a mandatory step. Accuracy assessment is just for quantifying whether any pixel has been misclassified or any pixel has been missing. Thus, while doing all these processes, I have shown the technique of mosaicing, where many satellite images are mosaiced together to get a single image. While processing this mosaicing technique, some pixels may get missed. Or while downloading the satellite image itself, some pixel value may be missed. So, how these missing pixels can be quantified? How it should be in a particular range. That is, the accuracy should be in 85 to 90% range. Then only the output will be good. So in order to check this accuracy assessment also, we have an option in this SCP plugin in QGIS. So this user accuracy, we have two accuracy methods like user accuracy and producer accuracy. User accuracy quantify error of commission, that is misclassifying pixels, and producer accuracy like missing pixels. And how we could identify like if we personally know a particular area. So if Ernakulam district if it is very familiar to me, if I could identify like in this image I can see vegetation here, but I know there is that area is not vegetation, that is an area of water body. If I personally know that, I can correct those values. That is ground truthing. And if I know the correct geographic coordinates of that particular location, I can easily identify that area and can correct the pixel values of water body to that particular location. That is called ground truthing. So if we could identify like much missed pixels or misinterpreted pixels are there, we can rectify it by means of this ground truthing method. So this is the equation for user accuracy. That is the number of correctly classified pixel in a class by total number of pixel in a class. Class means Actually, in the land use land cover images, we can go for many number of polygons. That picture not here. Okay. Many number of polygons that we can draw over here. And that polygons represents a particular class. So each class and total number of pixels in a class is also countable, and number of correctly classified pixels in a class is also countable. So for user accuracy, this equation is already in the GIS platform. We are just clicking on user accuracy, it will give the value. This is actually what happening inside the software. We didn't go for any raster calculator and all for this purpose. So number of correctly classified pixel in a class by total number of pixel in all class. Some sort of slight differences are there in this case. And overall accuracy is total number of correctly classified classes by total number of pixel in all class. While we are clicking on this, we will get for agricultural land, because we have made polygons based on different types of features, like agriculture has a particular polygon, built-up area has a particular polygon. For each polygon, it has evaluated and accuracy has measured. And here we can see, like wasteland, the accuracy is much less. So there may be some misinterpreted pixel or missed pixels are there. In that way, we can identify whether the image is correct or not. So the producer accuracy is for state. And overall accuracy, it should be for good quality work, it should be between 85 to 90%. And more than 85% is more good for further processing of LULC. Now we can go for statistical analysis. That is, now we have seen the indexes, we have just seen the patterns, and we couldn't identify any percentage or like that, we couldn't get any quantitative value. For that, we are doing the statistical analysis. So one of the effective method, statistical method is one of the effective method to pinpoint changes in urban area, whether the sprawl has happened or not. So for that, actually, I'm taking the same example. So that Ernakulam district has been divided into different taluks for doing this statistical purpose. We have to get different type of zone. So how to divide a zone? It is easier to go for taluk boundaries. So this is study areas divided into zones, and the shapefile of each zone are separately extracted and clipped. And extraction and clipping, now we know what's the procedure. So shapefile of each zone has been clipped with the LULC map. And here comes the different types of zone. You can see 7 zones of Ernakulam are actually classified. And based on this equation, this is the Shannon's entropy method is used as a statistical tool for this particular study. We have yet another method, kappa coefficient, then Henderson methods. Many methods are available in the statistical tools. Here we adopted the Shannon's entropy, and these are the equation for calculating those things. And for that, we need zonal details. So Shannon's entropy will be calculated in such a way that if the value varies from 0 to log n, log n means n is a number of zones. Here the number of zone is 7. So value varies from 0 to log n, and if it is closer to 0, it represents compact distribution of built-up areas, and if it is closer to log n, it represents scattered distribution of built-up areas. And higher entropy value indicates that the sprawl has occurred. And we can fix a threshold value. Threshold value is some like it is a log n value. So if a city crosses its threshold entropy value, it is said to be sprawling city. That is the statistical method. So for that, actually, we have divided the entire Ernakulam district into different zones, and the total area has been calculated. The area detail we can acquire from the GIS itself for a particular polygon. If you are selecting, you have to get the total land area. The value will be getting in the attribute table. So the total area for each zone has been taken, and the built-up area also we can acquire by selecting the built-up colors in that particular polygon. We can get the built-up area also. So for total area, this much is the built-up area, and using this equation, we could get a particular value. And this is Shannon's entropy for 2030 and 2023. The calculation is shown. The log n value is 0.845. Log n means number of zone is 7. So it is 0.845. And according to this entropy method, it is states that if it is crossed beyond this threshold value is log n. If it is beyond this threshold value, that means sprawl has happened. Or if it is nearer to this threshold value, the sprawl can happen. It's nearest to urban sprawling border. Okay. So in the 2013, actually, the entropy value is 0.719. This it's actually safer side. This is in the urban growth side. And 2023, the value is somehow nearer to the log n value. That is 0.842. It can set like the sprawl has started. Okay, so this is the method how we can quantitatively analyze this built up growth has leads to urban sprawl or not. So in that way, we have compared this LULC 2023 data with already published data of 2006 and 2016 Ernakulam district. Already some studies have been conducted in so many journals we have referred. So in that, we could identify the area of agricultural land in 2016 was this much, and how it come reduced in 2016 and how it is reduced in 2023. So agricultural land has a drastic reduction from 2006 to 2023. In that way, we can go for another feature like built up area. It is drastically improved or enhanced, like 252.93 in 2006, and it get increased to 857.2. In that way, we can check. There are so many studies have been conducted, and so many publications are there in this area. So while we are taking a particular study area, data are plenty for comparing our data with the previous work. The forest area also we can see, and the wasteland also reduced. The water bodies is also reduced from 2006 to 2023. In that way, we can identify how this land use patterns have been changed in the past 20 years. So these are the percentages, how it is reduced or how it is increased based on this LULC data. So these are so based on this LULC image and based on Shannon's entropy values and all. In this study, 5 major areas of urban sprawl has been identified. That is compared to another region. Values from Vellore, Kodamangalam, Muvattupuzha, Kochi, and Parvur has actually reached the stage of urban sprawl. That is, the growth has taken place disproportionate to what the trend line suggested. This is what the outcome of this particular study. So by here, I am ending the session. Actually, if you have any queries regarding the procedures or process or importing satellite images, if anything, you can ask.
Participants may either ask the queries or post them in the chat box. Any queries, please?
One query is there, is it possible to identify underground water bodies through remote sensing? Actually, it's not deals with this topic. To my knowledge, actually, I'm not sure about this underground water bodies using remote sensing. Actually, water quality studies are being taken place for surface water bodies. Underground aquifer details, I'm not sure about it. I can go through such studies. Yeah, actually, groundwater quality analysis actually studies have been conducted in many papers using these geospatial techniques. Because if we have a particular image, groundwater quality analysis, I am not sure about, but the surface water quality analysis, here also BTech students are doing such project. Groundwater quality analysis, I don't know. I'm not much sure about that. We have to go for much geological details like aquifers. Then only we can quantify this groundwater quality.
Ma'am, there is a question regarding the internship. That's what they are asking, I think.
Internship provided by our institution, is it?
Is there any institution that provides internship to civil engineering students regarding aquifers?
To my knowledge, I am not sure about that. Regarding aquifers, right? I don't know. What resolution are advised for LULC? Actually, sir, it depends on which type of work we are doing. Actually, mostly preferable high resolution images. If we could download high resolution images, it will be much better, because if it is for doing some departmental or authentic work, we have to go for high resolution images. It is always preferable. But if we are doing for some UG projects and all, low resolution images are just required in order to just study the procedure of how we can obtain LULs. So depends upon the nature of work, we can fix the resolution. The resolution actually I have explained, like how much meter it is actually specified, that much meter is covered in a particular pixel value. So depends upon our intention. Like if we are more intended to work on this urban area, we have to get minor details, much more minor details. Obviously we have to go for high resolution.
Any more queries?
Our given images provide 10-meter resolution. For our studies, I have taken 15-meter resolutions I have just taken, and mostly I have taken the images from USGSR. Actually, it is more convenient to take. In Bhuvan, I think more number of tiles we have to import it, download. So I'm not sure 10-meter resolution is available or not. I think it's available. In the Bhuvan website, actually, the LULC patterns are also now available for our India, for whole India. Actually, the LULC pattern for recent years is also they have uploaded. I think the resolution images maybe there. Okay, I will put my mail ID here. If you have any queries or any help regarding this GIS, spatial data analysis and all, you can contact me. And in our institution also, we have providing so many training programs to GIS and remote sensing. So once we get, so in the next coming 6 months, in the upcoming 6 months, we are planning yet another training program. Surely I will intimate you and you can join.
So participants, shall we wind up the session if we don't have any other queries? On behalf of everyone present here, I hereby use this opportunity to extend our heartfelt gratitude to Dr. Prasija AV for her insightful session on GIS and urban sprawling. Her expert analysis illuminated the critical distinction between urban growth and sprawl, emphasizing that while growth refers to the expansion of urban areas and sprawl. Dr. Prasija ma'am's presentations underscored the importance of GIS in monitoring and managing urban sprawl, and I hope you all had a great experience while listening to her lecture, and many insightful things were also gained from the scene. We are truly grateful for the knowledge shared, ma'am, and the engaging discussion that followed. Thank you, Dr. Prasija ma'am, for the session that was both enlightening and thought-provoking. And thank you to all the participants for their active participation. We'll meet again tomorrow with yet another interesting session. So thank you all. Thank you, Prasija ma'am.
Okay, thank you. Once again, thank you all the participants for your patience listening and for your support. Okay, thank you.